Okay, let's get started. Again, a reminder that the homework number 1 is due on Friday, and also that practice set on substitutions is due Friday. Just also letting you know that all the lectures are being taped, and so if you have a burning desire, and I know some, and I can point out some who I know will, then you can see me on YouTube. But the links can be found on Blackboard. All right. Okay. So what we're going to start out today, and it's not going to last very long, is we're just going to look at a couple of additional things on substitution, and then we're going to go right on into some calculus with doing the derivatives of the ln function. So I want to look at this example right here that I've got up, the antiderivative of the square root of 1 plus x times x dx. And we want to evaluate this. And the first thing I want to point out, and it's an algebra thing that I don't want to see from anyone, is this. In this form, I know that we all know this, I cannot distribute that x like that into those two forms and say that this is the square root of x plus the square plus x to the 3/2 power or something like that. I cannot do that. So that's out. That's incorrect algebra, and we're not even going to go there. All right. So what I can do, believe it or not, is I can do a substitution here to evaluate this. I can take what's under the radical, 1 plus x, and let that be our u. And this is similar also. There's a couple things on homework, on the practice set that are going to work similarly that's due on Friday. And of course, when we do that, du is equal to dx. But what we get here, and you say, well, gee, I don't see anything that I've gained from doing this. But we really have, because we can take that first equation, u equals 1 plus x, and notice that if we subtract 1 from both sides, we get that u minus 1 is equal to x. So we can transform this antiderivative into the following. We can replace the square root of 1 plus x by the square root of u. We replace our dx by du. And then we can replace x by u minus 1. Like this. Now what we can do with this then is we can distribute in order to get two terms. So this is u to the 1/2 power, right? The square root of u. So let me distribute. U to the 1/2 power times u to the first power, add the exponents together, that's going to give me u to the 3/2 power. Okay. And then minus, and then u to the 1/2 power times 1 is minus u to the 1/2 power, du. So now I have something very manageable because I was able to distribute by making that substitution, and now it's easy to go from here. In fact, I'm only going to go one more step with this. Then we just do add 1 to the exponent, that's going to be u to the 5/2 power. Remember, we have to divide by that same raised exponent, but that's really the same as multiplying by the inverse. Do not forget that. So that's our first antiderivative of the first one, and then here is u to the 3/2 power. Again, we have to divide by the 3/2, but that's the same as multiplying by 2/3. all right? Well, I might as well finish this. So then, and then it's plus capital C, and then finally we just replace the u with what it's equal to. It's equal to 1 plus x. So we have 2/5 times parentheses 1 plus x to the 5/2 power minus 2/3 parentheses 1 plus x to the 3/2 power plus capital C. All right. And I don't really care about any more simplification with this. With the algebra, you could take 1 plus x to the 3/2 power out. I'm not concerned about that. So that would be our antiderivative here. This kind of a substitution that we did here, you're going to see in a few more sections that we're going to have a whole section which has those kinds of substitutions in it. Okay, so I wanted to go over that. Any questions on that substitution? What seems to not necessarily work turns out to be a very kind of clever thing to do to make it work. All right, then this is another thing I want to let you know what my expectations are of you. Let's just say we have the cosine of antiderivative of the cosine of 3x dx. Okay. Well, we know that the derivative of the sine is the cosine, so we know we're going to have sine of 3x over here as part of the antiderivative. But what I'm going to expect you guys to do, instead of doing the whole u substitution thing, let u equal 3x, du equal 3dx, etc., is that I want you guys to realize that this antiderivative is just the number that we're going to multiply in front is just going to be the reciprocal of that number, 1 over 3, plus c. So that when we take, so you can always check it by taking the derivative. When you do the derivative of 1 over 3 sine of 3x, you get 1 over 3, derivative of the sine is the cosine of 3x, and then of course we have to use the chain rule, so the derivative of 3x is 3, and of course we get back to what we started with. So let me do a couple more of these, and this is what because I'm going to be doing, I'm not going to be, for these kinds of ones, I'm not going to be spending the time saying let u equal 3x or u equal 5x. I'm just going to be writing down the antiderivative for these things. So here's another example. Let's say minus 10 of sine of 5x dx. All right. So, all right. We've got the minus sign here. We know that the derivative of the cosine is the negative sign. So we know we're going to have the cosine of 5x over here. Now, instead of doing all this other stuff, I just have a 10. I've already accounted for the minus sign. So I just take my 10, and I know I have to divide by the 5, that is by the 5x, to get my antiderivative. So what I'm going to come up with, 10 over 5 is 2. 2 times the cosine of 5x plus c is my antiderivative, without doing all that writing down of the u substitution. Okay. Another type of thing, say, would be, we've already talked about the e function, the exponent function. Well, something like this is a similar thing. We know that the derivative of the exponent function is equal to itself. So my antiderivative is going to have e to the 3x in it. But just instead of doing that whole u substitution business, just take that number that's in front of the x, and I'm going to do its reciprocal in front. And that is going to give me the antiderivative. So you're going to start seeing me for these what I consider very simple substitutions to just be doing that instead of writing the whole scenario out, all right? And I expect you guys to, it'd be better for you as far as doing future homework to get used to, at least for these simple substitutions, to get used to doing this, all right? And you can mentally always check your answer If nothing else, of course you can do it in writing, but you can also just mentally look and check that the derivative of what we get here is equal to our original function. What I'm saying is, unless, of course, you can always do it on paper, but we can check it. We have a 1/3 e to the 3x because it's its own derivative, but then we know we have to do that chain rule times 3, and so the 3's cancel out, and we get back to what we started with. All right. So this is just an FYI for what I'm going to be doing, and what I think would actually be better for you guys to start getting in the habit of doing for these very simple substitutions. Okay? Does anybody have any question on that? Because it'll really make life easier for you. Yes, Jenna?
What is it like in I just kind of love the book of this
You mean like, okay, you're talking about for the, say, for a sine or a cosine, or for the e? It actually doesn't matter. Okay, let's say that we're given this, where a stands for a number, right? Okay, it's the same principle, Jenna. We just, again, we know it's its own antiderivative, so we have e to the ax, but just take the reciprocal of the a, 1 over a. Okay, just like we took, say if the a were a 5, this would be 1 over 5. Except they're just using a letter to stand in for a number, okay? And of course, plus c. Any other questions on that? The quicker you get in that habit, the easier life will be for you as far as doing homework, etc. What do we have here? We have something. Oh. And the answer is no, but we'll have to figure it out later. Eureka's got, I don't know, I'll have to ask our tech person, Muha, what I probably need to click on something here that I'm not clicking on to see them. Eureka's got a camera up in their room so that I can see them. So I can keep tabs on them because I hear they've been pretty unruly, and that way I can check out what they're doing. But right now I can't, but we'll figure it out. Okay. One other thing in this section here, and then we'll move on to the derivatives part of things. This is still in the very last part of this section, 6.3, yeah. So still hanging on to dear life to section 6.3. This is called a change of base formula. So in particular, this is the fact that you guys need to remember, so putting a big asterisk there by this fact. The log base A of x is equal to the natural log of x divided by the natural log of A. All right. And I'll even do a quick proof of this to show why this is the case. Proof. Let's say, the variable y equal log base A of x. Okay. Now let's do the spiral business here, or in other words, log base A of x equals y. Let's do the spiral, a to the y power, finish it off, equals x. So that's our equivalent exponential equation using the spiral, okay, that we talked about before. All right, now take the natural log of both sides. So we take the ln of a to the y equals the ln of x. And now we're going to use one of those log expansion properties where if we have an exponent here, we can bring the exponent down in front. So this is y times the natural log of a equals the natural log of x. Just using one of the log properties. And now divide both sides by the natural log of a. So we come up with y equals the natural log of, equals the natural log of x divided by the natural log of a. And of course, y is this thing right up here. So we're showing that those two are equal to each other. Now, let me just do and say one example here of this, how this can work. Let's look at the log base 8 of the number 5. Okay, this is equal to the ln of the 5. That's the x here that we have, that we're taking the log of, divided by the natural log of the base 8. Which again, here we have the natural log of the base 8 in the denominator. So that log is equal to the quotient of those two things. You can do all that on your scientific calculator, and you come up with approximately 0.7739 as your answer. So this particular formula up here, we will be revisiting this again when we do derivatives. So I want you guys to, that's one of those things that I'm putting on that list of things that you need to know for the first test, all right? So, okay. Now let's, if you don't have any questions on that, I want to move on to the next section then. Section 6.4. Now we're back to some calculus here with this section. This section's about taking the derivative of log functions. And the first thing we have is this fact. And again, a fact that you need to remember. The derivative of the natural log of x with respect to x is equal to 1 over x. In fact, we're going to do a quick proof of this to show why this is the case. So, proof, let's call the ln of x, let's just label it, let's just say y is equal to the natural log of x. All right. Then, or in other words, the natural log of x is equal to y, either way. And then let's do the spiral business on this, like we kind of did with that last proof. And what is the base that is down here that I don't write? What is the designation for that base? For the E, right, 2.718 approximately. So that base is really down there, even though we don't write it. So using the spiral, we have e to the y power, finishing off the spiral, equals x. Okay. So that's our what's called our equivalent exponential equation to this, using that spiral. Now, what we're going to do here is called implicit differentiation, which is something that you guys looked at in Calc 1. Implicit differentiation. All right. So we're going to take the derivative of e to the y we're going to take the derivative of both sides of that equation with respect to x. So I'm going from e to the y equals x down to the derivative of e to the y equals to the derivative of x with respect to x. Just doing the derivative. Now the right side of this is easy. The derivative of x is equal to 1, right? So the right side is easy. The left side we have to use the chain rule. Okay. The derivative of the exponent function, first of all, equals itself. So we have e to the y. But then in turn, we have to use the chain rule times the derivative of that exponent, y, with respect to x. Chain rule. All right. So we have e to the y times derivative of y equals 1. Now let's divide both sides by e to the y. We have dy dx equals 1 over e to the y. We're almost finished here. Remember, way up here, that e to the y is equal to x. So I'm just going to replace e to the y down here with x. So I end up with dy dx is equal to 1 over x. And that is exactly what we were asked to prove, because y is equal to the natural log of x, or the derivative of the natural log of x with respect to x is equal to 1 over x. All right. So, something to remember. All right. Now, from that, we know we can always use the chain rule with derivatives. So, chain rule let u equal to some function of x, then the derivative of the natural log of u with respect to x is equal to 1 over u. That's from the main formula, 1 over u, but now we have to do the chain rule times the derivative of u with respect to x. Or we can write it this way, 1 over u times u prime of x. I like to squish this together into a single quotient, u prime of x divided by the u. This is also something you need to be able to know. One thing that we have with this formula that is very helpful to remember is this. The top is the derivative of the bottom. So this is really the derivative of the inside function, which is u, derivative of u, divided by the inside function itself. All right. So let's do some examples so this becomes more concrete to us. Examples. Let's look at, say, the derivative of the natural log of 1 plus x to the third power. Okay. Well, this is equal to 1 over 1 plus x to the third, we do the reciprocal of that inside function, times, remember the chain rule, times the derivative of 1 plus x to the third, which is 3x squared, because the 1 goes to 0. And again, I can combine this into a single quotient, and I get 3x squared divided by 1 plus x to the third. So this is something we can just get right here to this. This is the derivative of the inside, and this is the inside function itself. All right, that's the formula with the chain rule. Are we okay with that example? Let's just do a couple of more here with this. How about the derivative of the natural log? Now the inside function is going to be the sine function. Okay, in fact, let's just do this in one fell swoop. We know that the top is going to be the derivative of the inside function. So the derivative of the sine is the cosine of x, and the bottom here is just going to be the inside function. Okay? So we have cosine of x divided by sine of x, which is a perfectly correct answer, but if we want to just make this, we could actually make this just into a single function, because remember, cosine divided by sine gives us the cotangent. Right. Okay. The cotangent of x. because this is the adjacent over the hypotenuse. This is the other side over the hypotenuse. And when we then do the algebra, we get the adjacent over the opposite, and that's the cotangent, okay? All right. Another one, we're going to do two more here. Derivative of the square root of the natural log of x. All right. Well, we know that, let's get rid of the radical notation. This is the derivative of the natural log of x in parentheses raised to the 1/2 power, right? The square root is the 1/2 power. And then we're going to do the chain rule. We bring down our 1/2. We write our ln of x. We decrease the exponent by 1 to a negative 1/2. And then to finish the chain rule, we have to do the derivative of the inside function. Derivative of the ln of x is 1 over x. So this is what we get. We could, if we wanted to clean this up a little bit, which I'm not really that worried about doing, but we could write this as 2 times x. We could flip this down into the denominator as in the denominator the square root of the ln of x. But I'm fine actually with just the answer written like that. That's perfectly fine with me. So the chain rule works in all kinds of ways. And the last one, on the face of it, looks like a horrific kind of problem. I love that, horrific. But it's actually not so bad. Let's look at this one. The derivative of the natural log, and then we've got a heck of an inside function in here. We've got x plus 1 divided by the square root of x minus 2. And we're doing this derivative. All right. Now, remember the normal rule is this. We take the derivative of the inside function, and I'm not even going to do it. I'm just going to put, this is, if you want to strong arm your way through this, this is how you would do it. Divided by the inside function itself. And that's a mess to calculate. Easy to make an arithmetic mistake. Let's do it another way. Before I get, let's just first of all go back to what we're taking the derivative of. We're taking the derivative of the natural log of one expression divided by another expression. So I can use, this is where you can use those log rules to expand this out. This is equal to the natural log of the top expression minus the natural log of the bottom expression. So already you've got things, you're getting things a little bit more user-friendly. And I can even go one further step here. This thing right here, so this is the natural log of x plus 1 minus, now it's the natural log of the square root of x minus 2. So this is really the natural log of x minus 2 raised to the 1/2 power, because it's the square root. I can do one more simplification here, expansion. I've got a power here of 1/2. I can bring this down in front as my final simplification. So we have then ln of x plus 1 minus 1/2 times the ln of x minus 2. Now, we haven't done the derivative yet. All we've done is make our function a little bit nicer. Now we do the derivative. So what we're doing the derivative of, let's do it, we do it a term at a time. It's going to be the derivative of the first term minus 1/2 times the derivative of the second term. So we've been able to expand it out to get two easier terms. Well, let's look what we get, go term by term and get the derivative. The first one, is going to be x plus 1 in the denominator, but what's the derivative of x plus 1 for the numerator? 1, yeah, it's just 1. So that's our derivative of the first term, and then we put in our minus 1/2, and then let's do the derivative of the second term. Okay, again, we put our inside function down in the bottom, x minus 2, and again, what do we get for the derivative of x minus 2? We also get 1. So here's our answer. Doesn't look too horrible after all. If we tried to work it the original way without doing any log properties, we'd end up with, it's just not pretty, okay? So let's not go there. Let's take advantage, if we can, of these log properties to make our function be a little bit nicer. Okay, so there was a reason we went through all those log properties, okay, now. All right. So we went through some examples here of derivatives of the natural log function. What I want to look at next is this one. Let's look at this function f of x equal to the natural log of the absolute value of x. So we know with the absolute value, we have the two, what I call like goalposts or something around the expression. Now, let's figure out another way of writing this f of x. If x is bigger than 0, if x is a positive number, what does the absolute value of a positive number equal? What's the absolute value of 5 equal? 5, right. So if x is positive, the ln, the natural log of the absolute value, is just equal to the ln of just the x. All right? All right. Now, what happens if x is negative? What's the absolute value of negative 5? 5, right? Because it's always a positive number. So if x is negative, we have the ln of minus x, because that, when it's negative, the absolute value equals the negative of the function. All right? Okay. Let me ask you a question here. Can x actually equal 0? Can we have the natural log of 0? No, we can't. Natural log of 0. Remember how this natural log function works, just this graph of it. Here's where x is equal to 1. It goes slowly up this way, then it goes down, 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 down. It never touches that y-axis. So x equals 0 is not on the graph. So we can't do the natural log of 0. Okay, so here we basically have showed what our function is if x is equal to 0 and what it is if x is less than 0. Okay, so let's look at each of the cases. If x is bigger than 0, then f of x is equal to the natural log of x. So the derivative of the function is equal to 1 over x, just from what we had indicated earlier. Now let's look at the second case where x is less than 0. In this case, f of x is the natural log of the negative x. So let's get its derivative. Okay, so in the denominator we put the inside function, which is negative x. And in the numerator, what's the derivative of negative x? Negative 1, right? So we get negative 1 divided by negative x. Well, I can cancel out those minus signs, and I get 1 over x. So in both of these cases, my derivative is the same thing, 1 over x. So I can come up with this, and I'm going to put another asterisk right here. Thus, the derivative of the natural log of the absolute value of x, either way we go, is going to equal 1 over x. All right? Okay. So, if we know that the derivative of something equals something, we can then look at the antiderivative. So let's go here. Let me get a new piece of paper. Okay. This implies that, let's go the other way. Let's look at the antiderivative. That the antiderivative of 1 over x dx is going to equal the natural log of the absolute value of x. We're just going in the other direction, plus c. Important, right? Of course, another way we can represent this is, instead of writing 1 over x, it could be written as x to the negative 1 power. So you could sometimes see the antiderivative of x to the minus 1 is equal to the natural log of the absolute value of x plus c. All right. So we're going to work with this antiderivatives now for a few examples. And it's going to involve u substitutions. We can certainly say in general that the antiderivative of 1 over u du is equal to the natural log of the absolute value of u plus c. All I'm doing there is changing the x to a u, nothing else. Okay. So with that in mind, let's look at the antiderivative of x divided by x squared plus 1 dx. All right. And let's do a u substitution with this. Well, we probably want to have the u equal to the denominator, x squared plus 1. Because notice when we take the derivative, we come up with an x, which is what we want. So du is equal to 2x dx. All right. Now we examine what we have in our integral here. We have x dx. So I'm going to multiply both sides by 1/2. So 1/2 of du is equal to x dx. All right. Now let's try to see what this comes out to be then. Okay, I have the u in the denominator. X squared plus 1 is equal to u. And let's put, we have to put something in the numerator. Let's put a 1 up in the numerator. And then notice we have the x dx is going to be replaced by 1/2 times du. So let's put the 1/2 there and the du there. And this is, or we could write it as 1/2 times the integral of 1 over u du. And as a result, what we have is the antiderivative of 1 over u. We know how to do that now. So this is equal to 1/2 times the natural log of absolute value of u plus c, and then replace the u with what we had designated it as, 1/2 times the absolute value of x squared plus 1 plus c. Let's go up with this thing. A question for you guys is this. X squared plus 1, this expression that's right in here, is that expression ever going to be negative? So with this particular expression, I don't need to keep the absolute value sign, so I can just write it as 1/2 and just use plain parentheses, ln of x squared plus 1. All right. Before I do another example, I want to point out the value of let's just say the gap that this new formula fills in. Remember when in Calc 1, you were introduced to this antiderivative formula. X to the n power dx, doing its antiderivative, we increase the exponent by 1, and we divide by the same, plus our capital C, all right? And you were told at that time that this formula is only good if n doesn't equal -1. Because look what happens if n is equal to -1. We have -1 plus 1, that would give us a 0 over x, and then we have a 0 on top, which is meaningless. So this formula here now fills in the gap, that gap. We now can take the antiderivative of x to the -1 power, all right? Or 1 over x. Because if we do the old rule with it, we get garbage, we get nonsense, but now we can do it. Okay? Questions? Comments? All right, let's just move on ahead here then. Let's do another substitution here. Let's calculate, and we'll do a definite integral here from 1 to the number e of this integral ln of x divided by x dx. Okay. All right. So we're going to need to do a substitution with this. What do you suggest as for what we might want to set our u equal to in this one? Yeah. I think it was a tie here with you and Anna Lee and Eureka there, but I think you might have gotten to it a half second first. Well, said u equal to the ln of x. Because when we do the du, what's the derivative of ln of x? It's 1 over x dx. And that'll fit right in with the integral that we have. So I'm going to do the limits in just a second here. Let's just put in here what we end up getting when we substitute. The ln of x is going to be substituted with u. And let me just point out what another way of looking at this original integral here. I could also have just written out our original integral as the ln of x times, instead of divided by x, times 1 over x dx. And then this part right here then is what is going to be replaced by just plain old du. So now our integrals become something very simple. Okay, so do we see how I went from one to the other here? Using our new derivative rule that the derivative of the ln of x is equal to 1 over x. Now I need to look at my limits of integration here because this is a definite integral. So when x is equal to 1 here, u is equal to the ln of 1, and we're going to remember, we know that the ln of 1 is equal to 0, right? And then when x is equal to the top number e, u is going to be equal to the natural log of e, and we're all going to remember that that equals 1, right? ln of e is equal to 1. So our new limits of integration, bottom number is 0, top number is 1. And now we could hardly ask for a simpler integral to do now right here. Add 1 to the exponent, divide by the same. Our antiderivative is u squared over 2. Limits of integration from 0 to 1. I plug in the 1, I get 1 over 2, and then the other one zeroes out. And then this is our answer then, 1/2. Right. Let's look at another one where we're going to be using a substitution. And this is the antiderivative of the tangent of x dx. Okay. So what we need to do here is oftentimes and we're going to see this in later sections, oftentimes it's helpful to rewrite your tangent function in terms of sine and cosine. Let me put that down here. Often helpful to rewrite your trig function in terms of sine and cosine. Okay, so we're going to do that here. The tangent is the opposite over the adjacent, over 45, opposite over the adjacent. So that's going to be the sine over the cosine. So I can rewrite the tangent function as sine of x over the cosine of x. And now, if you know that the top can be seen as part of the derivative of the bottom, because we know that the derivative of the cosine on the bottom is negative sine. So having the u equal to the bottom function is going to lead right to 1 over u du as our integral. So let u equal the cosine of x, the denominator. Let's get the du. Well, the derivative of the cosine is negative sine. So, and we have sine x dx in our integral. All we need to do here is say either divide or multiply by -1, and we get negative du is equal to the sine of x dx, like that. And now we can do our replacement here. We can replace first of all, the cosine gets replaced by the u, and that's in the denominator. So let's represent it as 1 over u. And then the other part, the sine of x dx, well, that can be replaced by minus du. Let me put the minus right there, and let's put the du right there. Okay. You okay with that? Oh, yes. All right, and then we can do this, then becomes an easy integral to do. We keep our minus sign here, but what's the antiderivative of 1 over u? It's the natural log ln of the absolute value of u plus the capital C. So don't drop the minus sign here from your antiderivative. All right, then let's go on and replace the u with what we had set it as. So this is minus the natural log of the absolute value of the cosine of x plus c. Okay? Okay, this is a perfectly fine answer, but I can use some rules of logs to even make this maybe a little bit kind of nicer answer. Any suggestions on what I can do here to use a log rule to write it differently? Yeah, bring the -1 up to as a power. Remember, we can do that, bring that minus up as a power. So I can write this then as the natural log of the absolute value of cosine of x, but then I'm taking this minus and making it a power here. So that becomes -1 power plus the capital C. Now, let's look at this absolute value of cosine of x to the -1 power. Well, anything to the let's just go anything to the -1 power is equal to 1 over that something. You can put it down in the denominator to the first power. So over here, this absolute value cosine of x to the -1 power, I could write that then as 1 over the absolute value of cosine of x. Okay, just using rules of exponents there. And so this is now what we're taking the natural log of. So, does anyone remember what trig function is the reciprocal, what 1 over the cosine equals as far as trig functions is concerned? The secant, right. So this can also then be written, finally, as the natural log of the absolute value of the secant of x plus capital C. And for some of you who sometimes feel like you're overwhelmed by things to memorize, let me humiliate myself by telling you this little story from back in high school or something. Well, we had all this trig stuff, and so I remembered that the secant and cosine were reciprocals of each other. I remembered it up here because in this way, cosine starts with a hard sound, and secant is a nice, softer sound. So they're kind of opposites of each other. So in my head, I then always associated the secant as the reciprocal of the cosine, all right? And then similarly with the sine, the reciprocal of the sine, which is a nice kind of soft sound, is the cosecant. So I remembered that the sine and the cosecant are reciprocals of each other that way. All right. I also, while I'm at it, I also remembered that the sine was opposite over the hypotenuse because sine equaled sin, and I wanted to keep that away because I was a good Catholic boy. All right? So anyway, those are some of the ways that I remembered some trig things, because there's a lot of stuff to remember. All right, so we can therefore say this. Okay, so what we have found with this particular example is this, that the antiderivative of the tangent of x is equal to the natural log of the secant of x plus capital C. And although you can derive this through this whole process, it might also be a good thing to somehow try to keep in your memory bank also. So that's why I put a couple of asterisks by that. All right, what do we want to go on to here next? So what we've seen here, we've seen the derivative of the natural log is 1 over x. We've used the chain rule with that. We've then seen that the antiderivative of 1 over x is the natural log of the absolute value, and we've used some substitutions with that to get antiderivatives. So why don't we take about no more than a 5-minute break, and then I want to go on with this section then. So according to that clock, it would be 5 after. Remind me once you first put your product.
Hey, did you ever get your question answered by the homework?
Yeah, okay. You did? Okay. All right.
Was one reason and then you have the last three the virus because of the concern. That's one thing.
Yes, sir.
I wasn't really sure how to say that it was one-to-one, so I had to draw it. Just say it activated.
Okay.
Activated.
Okay. That's fine. Another way to do that is actually this. This is the function, right? X minus 2 to the right-hand power, where are they saying A is bigger for A equals 2? Okay. All right. So one thing, as far as the one-to-one is concerned, let's look at the derivative of this. So this is 1/2 times x minus 1 to the -1/2 power doing the derivative. Which is the same as 1/2. Let's put this in the denominator as the square root of x minus 2. All right, this is positive. This is going to be positive, so it's bigger than 0. So therefore, it's increasing, which means it's 1-to-1. That's another way to do it. Horizontal line test is fine also. Okay, that's my That can happen. Yes, sir. Okay, that's fine. Oh, that's okay. Well, I guess let's get going again then, folks. It is a quick 5 minutes. It really is. Yeah. 5 minutes is It doesn't last long. All right. The next topic here then in this section is this thing called logarithmic differentiation. Okay, big words, but interesting kind of way to do a derivative in some cases. So let me put this down first of all. We can sometimes simplify, and that's a good word in my vocabulary, simplify the process of getting a derivative, if we first take the natural log of both sides. First take the natural log, ln, both sides. So I'm going to do a couple of examples here to show what we're talking about. Okay, example. Let y equal to, let's see what, x to the 3/4 power times the square root of x squared plus 1, all divided by 3x plus 2 raised to the 5th power. Oh, this looks fun, doesn't it? Okay, so of course you could slug through this by doing the quotient rule, all right? And slogging through it is more like it. There's an easier way to do this one. Let's take the natural log of both sides. So natural log, so we'll have ln of y equals ln of, let me just put the whole thing in parentheses here, equals the ln of that. Now, well actually let me write it down. Okay. Except I'm going to write it a little bit different. See, x to the 3/4 power, let me rewrite x squared plus 1. Let's put that in parentheses to the 1/2 power. Let's at least get rid of the radical notation. All over, in parentheses, 3x plus 2 raised to the 5th power. All right. And what we're going to do here is similar to an example we did when we were looking at expanding logs. Let me just put this in kind of a box here. We had some kind of an example like the natural log of x to the 3rd y squared over z to the 4th, where we expanded that thing out, all right? And what we could do then is we basically could expand it out as 3 times the natural log of x plus 2 times the natural log of y, that's the top part, minus, then we have the bottom part, minus 4 times the natural log of z. Now I skipped a lot of steps in between here. If you look at the example we did, maybe I shouldn't have skipped all those steps. Let's look at, this is going to be the ln of x to the 3rd plus the ln of y squared. Because those are multiplying each other, I can add the logs minus the natural log of z to the 4th. And then put the exponents in front. All right? We're going to do the same kind of thing with what we have up here on the right side of our equation. So let's go back to our problem here. So we have the natural log of y is equal to, now let's expand this right side. Okay, I've got this exponent of 3/4, let's put it in front, times the ln of x. Okay. Then, because these are multiplying each other, I'm going to have a plus sign. And then I can take down this 1/2 here as an exponent times the natural log of x squared plus 1. Then finally, I have the expression in the denominator, so I have to subtract off, minus. I have an exponent of 5 here. I can put that in front times the natural log of 3x plus 2. So I've been able to expand out that whole right-hand side. We okay with that? Let me just, again, let's just do this here that I did before. We can say, let's go back up here. This is the ln of x to the 3/4. Since they're multiplying, I add the log plus the ln of x squared plus 1 to the 1/2 power. Then because this is dividing, I have to subtract, and then the ln of 3x plus 2 raised to the 5th power. And then I do the next step, bringing all those individual exponents down, and I come up with what I had written right above it, okay? So I kind of did 2 steps in one with that first one. So we have this big, long expression here, okay? What do we want to do with it? Well, what we're asking to do a derivative here, so I'm going to take the derivative of both sides. With respect to x. And again, this is called implicit differentiation. But what I'm really doing is just taking the derivative. Implicit differentiation. Okay. So let's do this here now. Let's go up here, getting a little far down on that. Okay, so we have the derivative of the natural log of y dx is going to, and let's just do individuals, we're going to have equals the derivative of 3/4 times the natural log of x, that's the first term, plus the derivative of 1/2, the natural log of x squared plus 1 with respect to x, that's the middle term, minus 5 times the derivative of the natural log of 3x plus 2. All right. Okay. So what's nice about this with the natural log properties is we've been able to expand one really awful expression into a series of better ones. Okay? All right, now let's figure out what's that derivative of the natural log of y. We have to use the chain rule here. Well, we know that the derivative of the natural log of y with respect to y is 1 over y. But then we have to multiply it by dy dx for the chain rule. Okay? So what this is this first part is the derivative of the ln of y with respect to y, and then we have to multiply it by dy dx for the chain rule. Okay, so that's our left side. Now let's go term by term and get our derivatives on the right side. So here we've got a 3/4 that we've got to keep, and the derivative of the natural log of x is 1 over x. So that's our first term. Now let's go to the second term, plus. We've got a 1/2 here we've got to keep, and we want to get the derivative of the ln of x squared plus 1. Okay, our rule is we put the x squared plus 1, the inside function, in the denominator, and in the numerator we put its derivative. So that's 2x. All right. And then we have our third term, minus 5. And we do the derivative of the natural log of 3x plus 2. Same rule. We put the 3x plus 2 in the denominator, and we put its derivative in the numerator, which is going to be the number 3. All right. So let me go up here and let's write this a little bit nicer, what we have. We now have 1 over y dy dx on the left side. Let's see, we can write this first term as 3 over 4x if we like, although it's okay the other way. Plus, let's see what happens here with the middle term. I think we can cancel out the 2's. Let's go on and do that. So we have x over x squared plus 1. And then with the third term, we can we have a minus, 5 times 3 is 15 over 3x plus 2. So we just did a little minor simplification there on the right-hand side. Now, what are we asked to find? We're asked to find dy dx. That was what we want to find. Well, notice we were almost there, because in this particular equation, we've got dy dx right there from the chain rule. So why don't I then, to isolate it, isolate dy dx on the left side, I just multiply both sides by y, and that'll isolate it. Multiply both sides by y. So we get dy dx equals y, and then in big parentheses, we write what we already had on the other side. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And we're almost finished. Say, oh, why? Let's go, remember way back at the beginning here, y is equal to that whole horrible expression, right? So what we're going to finally do in our last equation here is we're going to replace the y with what it was originally. So our final answer here on this is the following. Replace the y. So our y was equal to x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th power. That whole thing times, big parentheses, 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. So that's our answer, that's our derivative using this technique. All right. And of course, that's a pretty horrible looking function right there, but we don't have to simplify it any further, just keep it right there as it is. Okay, we're not worried about going any further with this. I want to do another example with this, but before I do that, any questions or comments on this one? You will see this on both homework and on the test, a logarithmic differentiation. And I think you'll even be told to use it, so that might also be a help right there. Let's do one more example here of this. Example, here we're given that y is equal to x to the square root of x powered. So that's kind of a strange looking function, because usually we're used to x squared or something like that. Here it's x to the square root of x, and we want to find the derivative dy dx. Now, you can see here, hopefully, that if we do the natural log of both sides, that square root of x is going to be able to be moved down. Okay? So let's take the natural log of both sides. Same thing as before. So we have the ln of y on the left, and on the right we have the natural log of x to the square root of x powered. Okay, so we're going to use that log rule where we can move that power down in front. So we're going to have ln of y is equal to the square root of x times the natural log of x. Okay. And then we do the derivatives of both sides with respect to x. Derivatives of both sides with respect to x. All right. So on the left side, so we're going to have 1 over y. This is going to be the derivative of the natural log of y with respect to y. And we have to use the chain rule then times the derivative of y with respect to x. So again, the chain rule. And of course, the derivative of the natural log of y with respect to y is 1 over y times dy dx. And then let's get the derivative of the right-hand side. And what do we have to be aware of needing to use, or what rule do we need to use to get the derivative of that property of the right-hand side? Product rule, absolutely. Product rule. So we're going to need to use that product rule for that right-hand side. Okay, so first of all, let's just take then the square root of x times the derivative of the natural log of x, which is what, 1 over x. And then let's do the derivative of the square root of x, which is what, let's see, that's x to the 1/2. The derivative of x to the 1/2 is going to be what? 1/2 times x to the negative 1/2, right? And that's going to be times then the ln of x, the product rule. The derivative of the one times the other one plus the derivative of the other one times the first function. Okay, product rule. So let's clean this right side up a little bit, because I think we can do that. How can I represent the square root of x divided by x as just a single quotient? Yeah. Well, yeah, square root of x divided by x. Yes, you're right. But how can I then just simplify that even further? X to the negative 1/2, it's fine. Or even 1 over the square root of x. Either one is fine, okay? Just using the rules of exponents, because this is x to the 1/2 power divided by x to the first power. You subtract the exponents to get x to the negative 1/2 power, all right? So that's our first term. Either one or the other is fine. And then this one, well, other one is fine too. I could also write this as 1 over 2, put this into the denominator as 1 over 2 square root of x, or x to the 1/2 power in the denominator, times the natural log of x. All right. All right, so finally then, so we've used the product rule. Are we okay with the product rule on the right side? So let's do the final step then. So let me just rewrite what we have. We have 1 over y dy dx on the left side. And let's write this right side as 1 over, it doesn't matter. I'm just going to write it as 1 over the square root of x plus 1 over 2 times the square root of x times natural log of x, like that. Okay. And then the final thing we have to do is multiply both sides by y. Both sides by y to isolate the dy dx. So that's, okay, so we have dy dx is equal to y times 1 over the square root of x plus 1 over 2 square root of x natural log of x. Okay, we got that. But we want to then write the y as how it was given initially. We go back, y initially was x to the square root of x power, so let's write our answer using that. So our final answer is x to the square root of x, which is our y, times, put big parentheses, 1 over the square root of x, plus 1 over 2 square root of x, times the natural log of x, like that. Be okay with that. You have a opportunity on some homework to do a little bit of that too. All right. All right. So we're almost finished with this section. There are two other things that I want to get across from this section about derivatives of the log functions. And these are things that you're going to see either on tests or homework, so we want to make sure we're clear on this. The first thing is this. Let's find the derivative of y equal to a to the x power, where a is some base greater than 0. Okay. Now, we've looked at y equal e to the x power, that specific base e, and we know that the derivative of y in this case is just equal to the e to the x function again. Okay, we've already looked at that. Here, a is any positive number, all right, as the base. So the fact here that we need to remember, asterisk here, is this, that the derivative of a to the x power dx is equal to this, a to the x power. So again, we repeat the original function, a to the x, but we have to then multiply it times the natural log of that base. So this is the formula, and I'm going to go through and do a brief proof of this so that I can prove to you that this is really the case. All right, so let's look at this proof, PF proof. Okay. Do you believe me when I write the following? That a is, where a is bigger than 0, a is equal to e to the ln of a. Remember that the exponent function and the natural log function are inverses of each other. So therefore, they kind of cancel each other out. So e to the natural log of a is going to go right back to a. All right. Same. Is there anything Keisha, is there anything I can help clear up, or that other people might want to know? I mean, okay. So a can be rewritten as e to the ln of a, because e and ln are inverses of each other. All right. So therefore, let's raise both sides to the power x. Raise both sides to the power x. So therefore, a to the x power is equal to e of e to the ln of a power raised also to the x power. I'm just raising both sides to the same power x. Now, that means a to the x power, well, let's look at this thing. If we raise a power to a power, we multiply the exponents together. So this left side can be written as e to the ln of a times x. Just power to a power, you multiply the exponents together. All right. So what I've done here is I've rewritten what I want to get the derivative of in terms of the exponent function e. Now let's do the derivative of both sides. So the derivative of a to the x is equal to the derivative of my e to the ln of a times x power. Okay, so now we're doing the derivative of the exponent function. Well, remember, the derivative of the exponent function, we're going to use the chain rule. I first just repeat the exponent function. So it's equal to e to the ln of a times x. You just repeat the function. And then I have to do the derivative times the derivative of the ln of a times x with respect to x. That's the chain rule I have to use. All right, let's figure out further what we've got here. E to the ln of a times x times, oops, we're getting low there on that, times, well, what's the derivative? The ln of a is just a number. So what's the derivative of the ln of a times x? Not n times x? Yeah, okay, it's like, we know that the derivative of 5x is 5, right? All right, so this ln of a is, what I'm trying to say, is like a number. Okay, it's a number of some kind. So the derivative of ln of a times x, we're just going to drop the x, and it's just going to be the number in front, which is the ln of a. All right, that's all. Just the same thing as when you multiply any number by x. You get the derivative, you just drop the x, and you just keep the number. So this is times the ln of a. All right. So we're almost there at our answer. Now we need to say, well, what if, so we have this. All right. Now let's go back to this thing right here. This first thing that I've got written here. E to the ln of a times x. We'll look right above here about 3 inches here, and we see that that is equal to, that's the same as a to the x power. So I'm going to rewrite this thing as a to the x power times the natural log of a. So what I have here then is that the derivative of a to the x power is equal to a to the x, but we have to multiply it by that factor of the natural log of a. So this, I'm again putting asterisks by that, right? All right, let's, I think we need to do a couple of examples here with this one so it gets a little bit clearer. All right, so examples. Let's look at, say, y equal to 10 to the x power. Okay, so this is our a right here. All right, that's the a. All right, let's use our formula to get the derivative. All right, so what the formula is you just repeat the function 10 to the x power, but I then have to multiply it by the ln of my base, ln of 10. All right, that's all we have to do. Or I can write this, I can multiply it in reverse. I can have ln of 10 times 10 to the x power. Either way you multiply it, it's the same thing. So here's one example of that rule, using a specific base 10 instead of just the letter a. All right, now let's look at one more example. With this example, we need to use the chain rule. So let's look at y equal to 10 to the x squared power. All right. Now, let me actually go back to this thing here. The derivative of a to the u power with respect to u is equal to a to the u times the ln of a. I'm just replacing x with the letter u, all right? Now we're going to use the chain rule here with this derivative. So dy dx here is going to first of all be, let's just do the derivative here, so we get 10 to the x squared power times, remember with our basic formula, we then have to multiply it by the natural log of the base. So this is my dy du, basically, we can look at it like that. But then I have to finish this off with the chain rule. I've got this x squared up here. I have to then do derivative of x squared dx. All right. So here we're letting u equal to x squared. So we have 10 to the u power times the ln of 10, but then completing the chain rule derivative of x squared. So we're going to get 10x squared times the ln of 10, and then times 2x for our derivative. All right. Okay. Maybe I ought to do one other thing with this chain rule here, just for the heck of it. A little concerned. Let y equal, say, 7 to the 3x plus 4 power. Let's put it like that. And we want to get y prime. All right. So y prime is going, and so this is dy dx that we're after. Well, with the chain rule, it's going to be dy du times du dx with the chain rule. And in this case, u is equal to the 3x plus 4. All right. So we have y equals 7 to the u power then, if we represent the 3x plus 4 with u. So dy du then is going to be from here 7 to the u power times the natural log of 7. All right. And then times du dx, that's going to be times 3. Derivative of 3x plus 4 is 3. And then finally, we can just replace the u here. We have 7 to the 3x plus 4 power times the ln of 7 times 3. All right. Okay, so that's another example with the chain rule. Remember, it's peeling the onion. You go from the bigger function to the inside function to get your answer. Does anybody have a question here on this chain rule, particularly with this one here? We're seeing this as 7 to the u power, and then we're getting dy du, which is 7 to the u times ln of 7, but we finally then have to multiply by du dx, which is going to be a 3, chain rule. Okay? All right. Okay, so I want to do one other thing here. The last thing on this section is another derivative, and now this time it's the derivative of log base a of x. All right. Now remember, we've done where a is equal to the number e, we've done the derivative of the natural log of x already, and we found that that's equal to 1 over x, all right? Here we're talking about where a can be any positive number. Now, the fact here that you need to remember is this. The derivative of log base a of x is equal to 1 over x times the natural log of the base. And this is actually a very fast or straightforward proof here of this. Let us refresh our memory as to, with the change of base formula, that the log base a of x can be rewritten as the natural log of x divided by the natural log of the base. That's the change of base formula. Now we want to find the derivative of this. So the derivative of log base a of x with respect to x is going to be the derivative of, let's write it this way, 1 over the natural log of a times the ln of x. I'm just kind of spacing out the ln of x over ln of a. And we can get the derivative of this right-hand side. Natural log of a is some number. So I'm multiplying the ln of x by 1 over the natural log of some number. So when I do the derivative, I keep that number that is multiplying in front. So I start out with 1 over the natural log of a times then the derivative of the natural log function. Well, we know that the derivative of the natural log function is 1 over x. So we get our formula, 1 over the natural log of a times 1 over x, or just writing it all as a single term, 1 over x times the natural log of a. All right, so this formula up here, whoops, that's something we need to remember then. So the final thing I'm going to do then is just an example, one example of this last formula. And again, it's going to be using the chain rule. So if any of you are a little fuzzy on chain rule, you're going to just keep on seeing it and seeing it, believe me. All right, here's the example. Y is equal to the log, let's make it the log base 7 of 5 plus 3 sine of x. All right, so this is like y equals log base 7 of some expression u. All right. And we know then that the derivative of y with respect to u, just using our formula up there, is 1 over u times the natural log of a. I'm just changing the letters of the alphabet. So therefore, dy dx here is dy du times du dx. So let's get this down. So dy du then is basically, what do we have? 1 over my expression u, which is in parentheses 5 plus 3 sine of x in the denominator, 1 over u, times the natural log of 7, all right? And then applying the chain rule, we then have to get the derivative, multiply by the derivative of that inside function, times the derivative of 5 plus 3 sine of x. All right. Let's go up there with this. So let's just go through this then. So we have 1 over 5 plus 3 sine of x. Times the ln of 7 in the denominator. And then we do the derivative of our inside function. The derivative of 5 is 0. Derivative of 3 times the sine of x is 3 times the cosine of x. All right. And so that is then our, and we can of course write this with 3 times the cosine of x in the numerator. And that's our answer then, okay? So, questions, concerns with that last example using the chain rule? All right. Do want to point out, and this is a 5-hour course, and it's very homework intensive, and it's not, and I don't want to scare anybody off, it's not going to get any better. I mean, it's just going to be, I'm looking ahead to the next unit. There's a lot of stuff, all right? I'm not going to try to slam you with homework, but this class requires a minimum of 10 hours outside the classroom, outside of here, if you want to get a C in this class. I mean, a minimum of 10 hours outside the classroom. Oh, yeah. You'll see it, you may not have been required 10 hours so far, But when we get into the future sections, it's going to require that much work probably for you guys. Well, it depends, it all student by student, okay? I'm just looking at, I'm looking at the average student here, all right? And it's a 5-hour class. It's not a 3-hour class. It's almost 2 3-hour classes, all right? So you need to just expect that you're going to have almost twice the work of 2 other classes, all right? So I don't want to scare anybody. I just want a little reality check that this is what you're going to need to do in order to succeed in this class. It's not going to be something that you can just kind of come to school, whip off homework, and then attend class and leave, and life is good and you don't have to do anything else. It's going to be more work. Yes, Jenna?
Well, I have a question because, so the homework that you gave us on Friday is like stuff that we have now already covered. Can we have like the next?
No, it's not. Let's do this Friday.
Yeah.
What sections? Give me the homework.
And 6.1 and 6.2. But I'm saying like, can we have the next homework sometimes so we can start working on it?
Oh, absolutely. In fact, okay, thank you. Then I haven't formally handed out the next homework assignment because I didn't want you guys to say, oh my God, I've got another homework assignment on top of this one. Homework number 2 is already posted on Blackboard. You can go in there under homework assignments and post and print it out, all right? But I never have the homework assignment be something that, for that Friday, that's something that you just had in class on Wednesday. Okay, if you look at the sections here, because that's what I was taking exception at, what I thought you said. There's nothing on that homework assignment that's due Friday, except for that substitution stuff, which is supposed to be a review anyway, that we covered in class this week. It's all stuff from last week. So I give you enough time to do the homework. All right, so I'll see you Friday then.
And the other question is when you do the also Blackboard, right?
What's this now?
The written ones are on there, not just like Blackboard.
Oh, yeah, the scanned notes, yes, they are. Let me stop this recording and then I'll get to you. Enchanting class today, Dr. Smith. Boy, we've got some salespeople over at these high schools. They are. They're having a blast over at these high schools. I know they are. They're having a lot more fun than we are. That's just my imagination. Maybe.
And if I was taking this first time around, I might have a video.
Okay, so this is, I just worked through the whole question about 36 and 7 here, on some part B, on the derivative of F5, and they're asking us to it says an A.
Yeah, right. And it gives you the A. Here, let's look at this here. That's okay. This is section 6.1.
What I'm trying to do is,
She gave me an old version of this book.
I got
That kid Ranger, I swear. I have my own version at home. The right version. Yeah. Okay, 37. Okay, so our function here that we're given is 9 minus x squared. So this is the f of x equals 9 minus x squared. And then we're asked to, so here we're given that a is equal to 8. And I think we're asked to find then the derivative, are we asked to find the derivative then of the inverse function at 8? Yeah. Find the derivative of the inverse function evaluated at 8. All right. Okay. So what we first have to do is we have to figure out, okay, the formula is this. It's 1 over the derivative of the original function evaluated at the inverse value of 8. Okay. So the thing is, this is what we have to figure out. F evaluated at what number will give us the number 8, which means that F inverse of 8 will be that question mark. 1, right. So F inverse of 1. So if F inverse of 8 is the number 1. So this is 1 over the derivative of the original function evaluated at the number 1. So what's the derivative of this function here? 1 over, what's the derivative of that function? Negative 2x. But we're evaluating it at 1. Right? Okay. So this is our answer. Minus 1/2. Yeah.
Yeah, I was just hung up on what's the question? Like, here, what method is finished, isn't it? You don't understand. Versus,
Yeah, it is.
Versus it right here.
Now here it's just saying, okay, use theorem 7 to find this, which is exactly what we're doing here.
Right.
So this is actually part B that we just did.
Right.
Part C is calculate the inverse and state the domain and range of it.
The inverse and then.
Right. So part C is saying, okay, here we have y is equal to 9 minus x squared. Let's interchange the x's and the y's. Find the inverse. Solve for y. And we're going to get y squared is equal to 9 minus x, I think, if you flip things around. So y, and I think it's just going to be the positive values. Y is going to be the square root, and so that's our inverse function.
Right.
And then they're asking you then to, well, the domain of that 9 minus x has to be bigger than or equal to 0. That would be the domain. So therefore, x would have to be less than or equal to 9. All right, for the domain. I'm not going to get too hung up on the range.
No.
Don't worry about it. I'm not going to get hung up on the range. And then calculate this then just from what you got here in part C. So here then our x is going to be what we're told. Aren't we told f inverse of, we're asked to find the derivative of f inverse of 8, right? Mm-hmm. So let's get the derivative then, just using our regular rules. Let's get the derivative of this, not using that special, just using our rules. So this is going to be what? This is 9 minus x to the 1/2 power. So it's 1/2 times 9 minus x to the minus 1/2 power times -1. Chain rule, right? Okay. And then let's plug in, what do we want to plug in? The number 8. Plug in the number 8 here, and we're going to get minus 1/2. 9 minus 8 is 1 to the minus 1/2. Well, any 1 to any power is 1. So we get the very same answer, -1/2.
Okay.
Right. It's just asking you to do it 2 different ways.
Okay.
Yeah. I think I got all that.
Very good.
Go back in my head. So I have one more quick question.
Sure.
On 41 and
Is it the same kind of thing?
yeah, find the derivative.
Okay.
Yeah. All right.
A is equal to 3. All right.
0 equals 3.
Yeah,
Try to find,
so therefore our F inverse, number is equal to 0, right? Okay. F inverse of 3 is equal to 0. Let's get rid of this other stuff. Okay. Okay, so let's see, we're starting on, let's see, the 41. It's just asking me to find this, all right. So we know that the number we're looking at is 0, so it's going to be, so f, the derivative of f inverse of 3, its derivative is going to be 1 over the derivative of our original function evaluated at 0, right?
This is the part I think I was missing on this formula. I was trying to
Yeah.
get the derivatives first and
Yeah, use this formula here. So you can get the derivative of that function. It's pretty easy, right? Where's the function? 3 goes to 0, we have 2x. Derivative of the tangent is what? The derivative secant squared pi x over 2, but then we have to use the chain rule to get times pi over 2, right? And this is the 1. And then we just plug in our 0 here. 0 there. So what do we get here? The secant of 0 is 1 over the cosine. The cosine of 0 is 1. So the secant of 0 is 1, right? So this is going to be 1 over 0 plus 1 squared, right there, 1. And we have the pi over 2 go from the chain rule. So we have 1 over, basically 1 over pi over 2, I believe, right?
yeah, the answer is 2 pi.
And the answer, that is just the reciprocal 2 over pi. All right.
This makes some more sense.
Good.
Because I thought I was looking back at my notes and the steps you gave us, I thought was an explanation of the formula, but it was really more just the other way of doing it. And I think I was doing it the same way twice.
And also, I mean, you can email me questions too, although fortunately on Wednesday and Friday, we're not run out of the classroom. Monday's horrible. I have 10 minutes to dismantle all this stuff up here, get all my other stuff together, and because she's starting at 1 o'clock, or 12 o'clock, I'm sorry, it's horrible. But at least on Wednesday and Friday, both before and after class, I'm here early because I teach an earlier class. Now on Friday, unfortunately, I'm jammed. I've got my algebra class goes to like 9:45 on Friday, and then this class starts up at 10 o'clock. But on Wednesday, I basically have free time before class and of course after class. So hit me with questions. I'm surprised I haven't gotten more already, and I'm a little concerned that I haven't gotten more already, to be honest. I expect questions. I won't bite. Okay. So I hope I help.
Oh, yeah, definitely.
All right. Thanks. See ya.